Hey everyone, today we're going to solve question number 64 on the DeepML site, how to compute the Gini impurity from a set of classes. First things first, we're going to just define what Gini impurity is and how we actually get there you know, from the ground up. We want to build it, assume we know nothing about Gini impurity, and at the end we'll be able to program this completely from scratch, just with NumPy. Gini impurity is a very crucial element in the decision trees. So it's a very useful thing to understand. This way you can understand decision trees and eventually random forests. So Gini impurity is a measurement of disorder. It just measures how much disorder is in a list of classes. Now this might be a little complicated to actually internalize and understand. And here's the formula for Gini impurity. Again, we don't understand what any of these elements are, and you're not supposed to. We're going to walk through it and understand everything from the ground up. Example. Here we have a basket of red apples, and here we have a basket of red and green apples. And our goal is to measure how much disorder is in this basket. So let's think about this logically. Imagine we had a basket filled with red apples. I'd say there's zero disorder there because everything's exactly the same. But let's say so we're able to quantify this relatively easily. But let's say we had a basket with some green apples and some red apples. How do we quantify how much disorder is there? We know it's greater than zero because now there's green and red apples versus before we just had red apples. So let's try and think about how we would actually quantify this. So let's take a little test example. Let's say we had three elements in the same class, or let's say three red apples. We would assume that this would have an impurity value or a disorder value of zero. But we know that if we had this set 1 0 1 1, so two different classes, we'd assume that this has a higher disorder because now there's two different elements. So in order to understand this, let's try and quantify what we mean by disorder and what we want. So in the basic example, all the same classes, let's say we took how many ones there are divided by how many total elements there are in that list, and that would give us one because there's three elements in that class, and then there's a total of three elements in that class, so that would equal one. But that's not exactly what we want. We want this to be zero. So let's do one minus the this amount, and that would give us zero, and that would could be the starting of our formula to determine disorder. So let's try and apply this formula onto our slightly larger set. Here we have, okay, so this is for class 1. So for class 1, we take all of the ones. So we see there's three ones divided by the total length, which is 4, and that would be 0.75. And then let's say we did the same thing for the 0 class, so we take how many zeros there are. There's 1 0, and there's 4 total classes. That would be 0.25. The reason we don't stop here and just use these values to determine impurity is because 0.75, like, if there's more of a class, that should make it, then there's less disorder caused by that class. If there's just one, there should be higher disorder caused by that class. So we actually do 1 minus, similar to what we did here, 1 minus the probability of seeing that number in the main list. So that would be 0.25. So saying, the ones have a disorder value of 0.25, the 0 has a higher disorder value because, without the 0, we would have no disorder at all. So we get a value of 0.75. So now that you understand, so this is just how do we quantify disorder into, like, okay, how much disorder is class 1 bringing, how much disorder is class 0 bringing. Now the question is, how do we combine these numbers together in order to get a single value that determines how much disorder is in a list of numbers or in a basket of apples. So first thing I tried, at least, was like, okay, let me sum these numbers up together because that just seems intuitive. The issue here is we would just constantly be getting ones. No matter how many classes there were, we would always just keep on getting ones, and that doesn't help us with anything. So I was like, okay, maybe we should take the average. So if we took the average of these numbers, it's right here, we would get 0.5. And so we say, based on this information, this class, this list structure, this basket of apples, has a disorder of zero point 0.5. And that is higher than 0. So, it seems like a good metric to determine. So we basically would take the probability or the proportion of ones of one class, the proportion of the second class, and then we would average those amounts together. The issue here is if we have, let's look at another example. If we have three probabilities, so probability of it being in class 1 is 90%, class 2 5%, class 3 5%. If we take we take the average of this, we would get 0.33, and that's greater than 0, and it looks great and nice. However, let's say we had another class where it was equally likely to be in class 1, 2, or 3. We would also have a disorder amount of 0.33. And the issue here is that, you know, class, example 1, with the most of them being in zero point 0.9, has less disorder because, most of it's part of the same class. And, example 2 should have higher disorder because, if you randomly pick one out, the odds are pretty dispersed. Versus in this one, odds of you picking out a red apple would be, or class 1 would be relatively high. So to deal with this issue, we could try another method. Let's try weighted averages. So a weighted average is basically take, the sum of how many red apples there are or how many ones there are. So 1 times its probability, so 1 times 0.75, plus 1 times, so 1 is how many here, times the probability of, seeing that is 0.25, and that would be 2.5. The reason, and then we have to normalize this value because if we don't normalize it, it'll be very difficult to use this to in any general use case. So let's say we had a case with 10 different classes or 3 different classes. We want to be able to compare how much impurity is in each of those across different examples. So that's why we divide by 4 here, and 4 is just the amount of the total amount. And here we would get, 0.625, but we would take 1 minus that for the same reason we spoke about earlier, just because, this element, the first element, the 3 times 0.75, this should be account for less disorder than this element. So we actually do 1 minus 0.625, and we get 0.375. And this, we would deal with this issue we spoke about. This is just another walkthrough, a little simpler. But it would deal with this issue we spoke about earlier. Because if an element has the same, like, if an element had the same probabilities of each class, it wouldn't have the same impurity if you do a weighted average. So now the question is, why don't we use weighted averages? Why are we using Gini impurity, this formula, to compute the how much disorder is in a basket of apples? So it actually ends up being, I'm not going to walk through the proof, but it actually ends up being that weighted average is equivalent to the Gini impurity. So all the Gini impurity is a weighted average of the classes, and 1 minus that. You could, I'm going to put the notes in the description below. You could, work through the proof yourself if you'd like. I think it's relatively interesting and relatively easy and fun, but it ends up being the same exact thing. So now that you understand, Gini impurity from the ground up, literally from a small example all the way to the actual formula, we could work through, the solution programmatically. So first, let's assume we have a list of all, integers of all different classes. So for example, let's say we have y equals 1, 1, 0, 0, 1. So that's, you could say it's apples or pears or whatever class structure you want to use here. Our first task is going to be finding out how many unique classes are in that list. So one easy way to do that is just the set. Just create y into a set, and a set basically will take out every single unique element within the list. So it'll take out the 0 and the 1, and classes will now equal 0 and 1. So now we have a list or a set of all the classes. We're also going to set a few other starting parameters. So we're going to say n equals the length of y, which equals 5, and we'll set the Gini impurity to 0 currently. Now we're going to basically compute the Gini impurity. So right here we have a loop where we go through each element of the class and we compute the Gini impurity and add them up. So let's actually walk through a little diagram I have over here. So classes is 0 and 1 thanks to the set, and we would, the loop would basically take the first element, so that would be 0, and then it would be 1, and that element would be passed into y.count. Y.count basically counts how many elements of that value that were passed in. So here it was 0, how many zeros are in this list, and that would be 2, and that would be 2 divided by 5. And then once we finish that, this would be updated into the Gini impurity number. So the Gini impurity would equal this. And then we'd move to class number 1. So class number 1, we say, same exact thing. How many 1 classes are in Y? That equals 3, and then it's 3 divided by 5. And then we would add those values up together, and that would actually give us the Gini impurity. Or I guess that would give us the Gini purity. To make it impurity, you just simply do 1 minus that number. Now that you understand Gini impurity probably too well, you should easily be able to solve, this question on DeepML, which I'll leave the link into the description. Also, we have a new question 108, which you could also try out, which is basically a little more open-ended, and you could try and make a disorder method however you like. You could do Gini impurity, you could do entropy, you could create your own. But, whatever it is, try and solve these questions, because watching this video is one thing, but actually implementing things by yourself, actually really helps you understand and learn all these topics. So have fun, guys.